Today we have our second session of the LCSR Regular Seminar, and today as a speaker we have Alexey Neznanov, an associate professor from High School of Economics, from Laboratory for Intelligent Systems and Structural Analysis, and he will talk today on design of a statistical experiment and intelligent analysis of results. And Alexey, you will have about let's say 50 minutes for your presentation, and then we will have Q&A parts, and usually we finish about 7:30. The floor is yours.
Yeah, thanks. Excuse me. I'm very sorry, but I catch a cold, so I'm just ill, and so maybe some of my words will be not so good. Excuse me one more time. So I'll begin. The topics of my discussion and our discussion will be several main questions about the design of experiments and intelligent analysis of the results of experiments. These topics was discussed with our colleagues from HSE, and we have the plans to analyze some results of sociological surveys and maybe additional surveys and research, and so we have interesting knowledge about modern methods of data analysis and additional topics about the pros and cons about the experiments and quasi-experiments. So, firstly, I must say several words about the experiment design. First of all, we have the very different terms about the domain of experiment design and experiment research. First of all, we have the term experiment, of course, but in different domains the term experiment means different entities. So for me and my colleagues, we have very simple questions. First questions: have we random assignment and full assignment by the methodology of experiment design? If we have the answer yes, then we have the so-called true experiment or controlled experiment or randomized experiment. Then, if we say no, we have another question. So, is there a control group or multiple measures or multiple comparison of these groups? And if we have the answer yeah, we have so-called quasi-experiment, and in the field of sociological studies, in the field of politological studies and so on, we have very much such quasi-experiments and a little amount of true experiments. And of course, if we have answer no for this question, then we haven't experimented at all, but with entity as some research we called non-experiment. And so in experiment and quasi-experiment we have, of course, design, protocol, and the data. The data as input raw data, so-called conducted raw data, and the results. And we have several tasks from the design, conducting, supporting, and of course result analysis. All this process in the most interesting domains iterative, and if we have some iteration, then we have better and better design, conducting, and so on. So if we have some problem situation, then we have the goal to conduct some experiment. In which cases we don't need an experiment at all. Of course, in very frequent situation, we have so-called Cochrane's aphorism, and this is such Cochrane as Cochrane summary and Cochrane status, and before doing a test, decide what you will do if the answer positive and the answer is negative. In the case if you don't know what is the difference between the positive and negative answer, maybe you don't need an experiment at all, of course. Then we have so-called preliminary knowledge and preliminary design of experiment. Of course, if we don't have some assessment of criteria about the result of planned experiment, the experiment will be very bad, and in many situations this is the waste of time. Of course, also we need, after the design, the protocol, the formal definition of all aspects of experiment. And in my case, the most important aspect is the data types, data formats, and of course data sources. Then we have some interesting topics about quasi-experiments. The main problem with the quasi-experiment is that we don't have randomization or full or double blindness. Then we don't have the normal process of correlation analysis, of regression analysis, and so on. And so we must ask additional question. Not only the null and one hypothesis, not only the question about some result as a simple answer, yes or no, but the second answer. What if we have other items or people or patients and so on, and we don't conduct such experiment and don't do some actions? What is the result in this case? If we have two questions, one question about the result after conducting and the second the result without conducting, and we need also the pre-test and post-test before the conducting and after conducting, we have the ability to ask itself about the not correlation but causation. And this is the main difference between the true experiment and quasi-experiment. Then, we have additional properties. Of course, randomization and blindness are the very common properties. I think that there is no necessary about detailed talk about these properties, but stratification also very useful in practice of experimentation. And when we have two or more groups, then we may have additional distribution of risk factors or simply factors of items or people or patients and so on. And when we conduct the good experiment, then we need some uniformity between the distributions of some such risk factors in all groups. In this case, we have so-called all other equal parameters. Or maybe this is the ideal situation, and in the practice we can continue our investigation about risk factors and try to hold our hands on the uniformity of all risk factors. And of course we need the explicit, and of course we need to write in protocol inclusion and exclusion criteria. If we don't have such criteria in formal form, then we will have very big problems with participant or items, patients, people and so on. Standard representation of result table in the first section of result analysis is participation, yes, and then different numbers before the experimentation in the several stages of conducting, and so at the last stage of experiment we can have a very small amount of items relatively to the initial number, and so without the formal inclusion and exclusion criteria we don't have the normal situation with representing with numbers in the protocol. So then we can try to discuss the quasi-experiment, where we can have additional very interesting property, internal validity. So if we have some preliminary knowledge about not only hypotheses about events, but also the approximate knowledge for causation of some factors and other factors, then we in some cases have some internal validity of problem situation, and in other cases we don't have with validity, and so every experimentation will be not adequate to situation at all. So then I have the very interesting example of domain where we have the fully standardized methodology of conducting experiments of all types. This is very interesting. So we have not only all types of outcome, not all types of questions, superiority, non-inferiority and so on, continuous outcome, discrete outcome, but we also have experiment and quasi-experiment without several levels of blindness, without special randomization, and with very interesting additional requirements. So in evidence-based medicine we have so-called controlled clinical trials, and we have special support for this kind of trials. In other domains such as risk analysis and in financial marketing, or maybe in some task about software engineering, we have such methodologies, but not so wide level of formalization and more than 40 years of standardizing. And the standardizing process in evidence-based medicine for now hold it not only by ISO, International Standardization Organization, but also by special additional organization and societies for standardization. We have the hierarchy of studies or research, and on the top level we have so-called systematic reviews. For example, Cochrane systematic reviews we use meta-analysis, so meta-research on top of several trials. We have very interesting additional statistical analysis with meta-analysis, and we have evidence knowledge. Then we have critically appraised topics, and this is the results of successful research sample. Then we have randomized control trials as the basis, and of course some background information about the field of medicine, different ontologies as formalized knowledge about this domain, for example, international classification for diseases, international standards for anatomy, atlases, and so on, so on. Of course, we have the additional very interesting ontology about bioinformatics, about networks of metabolism, and so on, so on. And of course, RCT I already mentioned, and in the simplest case, we must say that RCT is a statistical experiment of special kind, with many standards and guidelines. So, in such cases, we have the schemes for conducting and full support infrastructure. This infrastructure consists of very different parts. For example, we have clinical registers, special formal databases for acquiring all information and data about the experiment. Not only the outcomes, not only the characteristics of items, patients in this case, but also we have many types of additional information in formal form. In modern clinical centers, we have very special workers and clinicians on the not only standard positions, but also managers for clinical trials, analytics, and so on. Here on the slide we have standard roadmap from the National Institute for Health Research, Great Britain, and we have the full picture of not only conducting but also ethical committees, special design approvals, and so on. I think that if we will have such guidelines and standards in the domain of sociology, then I think we will have many additional results about the processes of surveys, the processes of analyzing the background information, and so on. So, in every such experiments and all domains, we have 3 standard stage and 3 standard statistical methods, or maybe families of statistical methods. The first is preparing, tidying, cleaning, and organization the raw data as the input to our research methods. Then the describing of the data as a result of the experiment conducting, and this is a descriptive statistics. I think that all people here know this part of statistics very well. And then we have very interesting and not so common sense part of the statistics as inference statistics. Why? Because we have very different cases of methods of inference statistics. First, we need to say some words about the testing logic. In the almost all inference statistics methods, we have very big constraints. First, we have only yes-no questions, so only discrete outcome and hypothesis. Then we have some formal state of the world. If we don't have the description, formal description of the state of the world, then all inference statistics methods don't work at all. Then we need diagnostic indicators for hypotheses. If we don't have formal description of these indicators, then we also can't use the inference statistics at all. And then we have a problem. In the real world, all indicators, for example, have some sentiment, latencies, and so on, or maybe really the nature of some very strange distributions in the sense of statistics. And then we have distributions, have range that overlaps. In only cases on the first exercises in the course of statistics, we have synthetic cases, but in real world we don't have such cases, and so we have such standard table. I think it's very well known, and then the main parameters. These parameters in many situations didn't formally described before the experiment, and so we don't have a priori margins and a priori level of statistical significance. Of course, we always have some levels of practical significance, but the gap between the practical significance and statistical significance is very big. In almost all my trials, there was gap that I didn't know what to do with it. I asked experts, I asked clinicians, I asked finance experts, and so on, and in almost all cases there are no a priori knowledge about the margins and about the statistical significance at all. And so I had a very interesting situation. I need the margin and significance, but I try to describe it myself with my common sense. So, in normal situation, of course, we have normal distributions, but with normal situation is abnormal in real world. In real world now we have, of course, very interesting non-parameterized methods, but such methods in several cases are very hard to implement. Why? Because with normal distribution we have very well formed terms about the alpha, beta and other significance parameters. But if we have very interesting distributions, for example bimodal, or maybe with so-called hard tails, we don't have so-called tables, statistical tables. And now we need special kind of software for parametric statistics and for so-called simulation. So, on the phase of experiment design, in almost all practical situations, we need some simulation. Monte Carlo simulation, or maybe discrete time simulation with time series, or maybe different types of simulation. But then we have preliminary knowledge about behavior of our statistical model. Without this preliminary simulation, we don't have some good pros and cons for the statistical models. We have more than 3,000 of statistical models for standard experiments. 3,000. So, if we want to select one of these statistical models for inference analysis, inference statistics, then we need some considerations. And where we can find such considerations? Of course, we have some features of inference statistics. For example, we have consideration about increasing, decreasing the alpha, beta and significance levels, and increasing, decreasing the results of our analysis. So we can put different numbers and hold them, and write in protocol different numbers. Classical example, 101, 105, 1, excuse me, 0.1, 0.5, and 0.10. And then we have three cases of statistical significance, and then we have the some maybe metrics of variance of our results, and we can select one of these results. But without preliminary writing in the protocol, all such actions will be so-called student answer. So we don't have preliminary design, but have good answer. Why? Because we know some constraints about our domain, and then in almost all cases we can decrease the gaps between the bad real situation and our good assessment of this situation in the result analysis. And so in our reports we have good data, good results, good outcome. Why? Because we changed our design. And we have two main different schemes, reject support and accept support. And for the reject support we have more than the 500 different variants of models, and for accept support we have more than 2,000 of variants of models. But in all practical situation we simply select one of these variants, and then we have our analysis for such variant, and we have very simple formulas that takes us some sample sizes. In which situation we have two variants. One, wow, we don't have such samples, we need another design. Why? Because, for example, we don't have the money for our service, or maybe we don't have the people in the Moscow as a town, and so on and so on. I remember that in the last year we have the very good book about the common errors in Russian surveys in the political and sociological studies from a very good woman, but I don't remember the name. methodology estimates the ratio of non-adequate designs and not adequate results, and the ratio was between 80% and 90%. So this is our goal. Then, if we have the samples of the normal size, then of course we have type of analysis and different models for discrete outcomes, continuous outcomes, and additional questions. First, calibration of expert and calibration of instruments. This is a very interesting task because there are very seldom I read some interesting section in protocol about the calibration of instruments and experts. For example, in educational data science or educational data analysis, we have the problem of teaching. In the field of politology, we have the calibration of so-called politicians and experts in this field. In the field of psychometry, psychometry, we have the very interesting problem of inference between the doctor and patient. And so we have second question about the inclusion-exclusion criteria for these sample sizes. Classical case when we have input number of participants in groups more than the margin of the sample, but then after the exclusions of some items or participants, we have small sample, and sample analysis told us, wow, we sample inadequate. Then we have additional methods of data analysis without concrete links between the statistical model and the data. And this is our hot point, because in this point we have the ability to use additional data, not the data from the statistical model itself, but the data in the protocol, the data as the raw data considering while we conduct the experiment, and we have the different representational types of this data. Of course, early we have some texts. Then, of course, we have many numbers. And then we may have additional interesting data, relational data, structural data, networks, graph, and so on. And of course, we can have preliminary knowledge, informal, formal knowledge, for example, as ontology. And for now, we have the model methods for using all these data to support our statistical analysis. We can check our errors, we can check mistakes in the conducting, supporting, and so on. We can check the samples not only by descriptive statistics, but, for example, formal concept analysis, and so on. And of course, we have the new methods of preparation of the data. In the last year, we have the big impact of the language R on the whole methodology of data analysis and design of experiment. Why? Because we have special packages for R where some people implemented modern methods of data preparation and data analysis. For example, data tidying package for now is becoming more popular and more popular. Each month we have more and more articles about with data tidying, and in the modern MOOCs on Coursera, for example, we have special sections about these methods. Then,
What is the package called? ETL or
no, it's the package data tidying, so-called.
data tidying, one
Yes.
word?
Yeah, and this is an article about this package from the creator of this package. So Wickham, this is one of the main creators. So then we have for now more than 50 articles about only this package. But also with Spring we was have more than 12 different additional packages for data tidying. Why it's important for different domains? Because in various domains we have similar tasks for data preparation, but with different constraints. And this package and some successors have special tools with very simple syntax for implement with standard methods, but with different constraints. For example, we have special methods for work with dates. For example, in every standard from ISO 8601 to every local Russian date, USA date, and so on. We have special methods for working with exclusion criteria for sample preparation. We have a standard tool for grouping, and of course we have new generation of experiment design packages. In 2015 we have the very interesting situation in which all old packages have obsolete at all, and we have several new packages, but all these packages have a status of beta version. So we need to wait maybe 1 year, and we will have the full infrastructure for new methods. Then we have the huge maybe very big amount of different places where we can have mistakes. Why? Because each statistical model, each experiment design, and each data analysis method have different flows. So, very common errors in hypothesis testing. For example, correlation and causation. I think maybe 1/2 of all articles have very inadequate explanation of difference between these concepts, and so we frequently have the conclusion in articles with causation, but without any analysis of causation, and only correlation analysis. I think all of you have some examples. Then, confusion difference between statistical and practical significance. Of course, p-value may be every value, but when we have our preliminary knowledge about some domain, we have the knowledge about practical significance. And of course, also maybe one half of all articles have very flow explanation about practical significance. Then we have type 1 and type 2 error, but these errors exchange when we have AS rejection, rejection testing and acceptation testing. But in many sources we have errors. They say, for example, about AS testing and show me the type 2 error. This is a mistake. And of course, the very important phrase, absence of evidence is not evidence of absence, because when we have null hypothesis, one hypothesis, then we don't have additional hypotheses in the statistical model. But we need this hypothesis, because if we reject the null hypothesis, then we know only that we reject this hypothesis. We don't know anything about additional hypotheses. So this phrase is very hard to understand in many articles. For example, in last read an article by me about the PISA, about schools and the quality of education. Yeah, they just with mistake in the very common case. We have regression testing about the inference between culture and quality of education, and then we have in conclusion additional consideration about the results, because we have the rejections of null hypothesis and we have many paragraphs of text about our considerations without any statistical background at all. More interesting case: 15 common mistakes in conducting experiment. Very interesting. This is the last version after more than 10 years of preparing with list. For example, we have failure to specify the exact statistical assumption made in analysis. For example, normality. In many articles we didn't have the check for normality, but then we use statistical methods for normal distribution. I think in most papers this is the current situation. Or, for example, failure to examine for normality of the data as a descriptive statistics, not the consequence using some statistical methods, but simple descriptive statistics. Or the last one, failure to understand and use correct scientific language. Very big problem. And the very interesting aspect of this problem is about the mathematical language. Indeed, we have analytics with modern software, but the software has very interesting flaws. We have the button and we can click this button and we take some number. We don't have special analysis of constraints, requirements and consideration about the methods for taking this number. And of course, the very interesting failure to critically assess the prior literature. So it's a very interesting list. And the next one. This is the specific mistakes in statistical analysis. 10 top mistakes. The first one is very interesting. equivalence on the basis of non-significance p-value. This is the consequence of second from here, yes, and from the AS and RS testing. Then, using Pearson in all cases, and of course for ordinal data. It's a classical one mistake. For example, removing non-compliant patients from the analysis without additional inclusion-conclusion criteria. So, in many educational studies, we have groups of students, and then we have exams, and oops, our sample of students became smaller and smaller. But we don't have such points in the exclusion criteria. We don't write that we exclude the students after the exam with mark 0. It's a standard situation. Or maybe the last one is very interesting, using covariates with dependent change during treatment. For example, during the course, for example, during the survey. So, we have some, not only list, but guidelines. And the first one, it's very good reviewer's quick guide for the journals, yeah. And this is a very interesting one for Elsevier. I think that other journals also have such guidelines, but this one is very straightforward. So, we have guidelines, we have standards, but we also have the big amount of mistakes in modern articles. Oops. Then, we have knowledge-based analysis, but I don't tell anything about this. I think we can discuss it, because this is my topic of scientific interest. And so, I have additional knowledge about the special implementation of such methods. And then, we have the software. Of course, the last versions of it. And for now, we have very good comparison analysis. I have only several links, but I have the list of the comparison, and now we live in very good situation. We have many open source software. For example, we not have only R. We have also very interesting intelligent data analysis tools. For example, Veka, Orange, and for now we have the language Python, programming language, with very interesting additional packages for it, for not only programmers but end users, with good data analysis abilities. And not only statistical analysis, but only intelligent analysis. And not only numeral dates, but also for text data and structural data. Then we have the very interesting efforts by big companies such IBM, Microsoft and so on, for producing very simple tools for data analysis and experiment result analysis, such RapidMiner. For example, RapidMiner is the second tool by popularity. Why? Because there are no programming efforts at all. We don't have any special programming customization in RapidMiner. And so, we have only end users for this software package. It's very interesting, and in visual interface we have very straightforward methods for implementing the stages of analysis with standard pathways non-standard pathways, parameters, and so on. I can show this. And then we have new methods of visualizing of data. Of course, early we have matrix visualization and some visualization of graphs. But now we have so much visualization styles. So now we have so-called elements table of visualization algorithms, for example. And in my list of basic visualization methods, I have more than 50 special visualization methods. For example, we have some lattices, we have some normalized data, we have so-called self maps, we have mind maps, cognitive maps, and so on, so on. And many of these visualization schemes became more and more formalized, and so in automatic way we have an ability to build such visualizations. And I'm sorry, but firstly I prepare the Russian presentation, and so after it I translate it in English, and so I have the part of presentation in Russian. I want to say about the time.
7 minutes
now,
left.
Excuse me?
5 or 7 minutes left.
So, the most interesting case in the last part of my talk is about current projects. For example, the first very interesting sample, maybe it will be interested for this domain. This is the optimization of processes and optimization by statistics, but not the classical statistics, but time series with additional inference between the resources and patients in this situation. And we have special methods, their programming implementation, and of course experts mentioned about the business process optimization, clinical process optimization, and so-called hospitalization trajectories. This is the next project. Yeah, optimization of resources. Not only the time series where the main variable is the time to come for patient, but the using of resources for some unit of time, day, hour, and so on. Other very interesting sample is about the different types of data using in conjunction with each other for represent the very complex data. For example, hospitalization trajectory is the path of a patient from the some first point, some disease, and between clinical centers, between doctors, between different types of therapy, between different surgeries, and so on. We have the structural data about the path itself. Then we have textual data in form of anamnesis, catamnesis, and so on. And then we have a lot of numerical data. And for now, we have the methods for translate all this data in one special structure called pattern structure, and using all data together for modeling the such trajectories. Different case is the modeling of software construction. Another case, the so-called CALS system, continuous acquisition and life cycle support systems. For example, when we have Airbus and we have so many types of details, we have so many types of industries and so on, and we can consolidate all this data in some complex structure and analyze some behavior of these complex structures. For example, we can test hypotheses on these complex structures, and we can find additional knowledge in form of some concepts or maybe additional entities. For example, in this hospitalization, we didn't have any information about the excuse me. Сейчас я наговорю реально причина.
Cause.
Yeah. About the causes of some transportation between the centers, but when we have such complex data, then after knowledge discovery technique, we have these causes as the latent knowledge, and so maybe doctor in the next center don't have the formal description of causes, but after the data analysis he have some consideration about such causes, and so this doctor have really additional knowledge, because in raw data we don't have in explicit form such knowledge. So, for example, in educational data mining, when we analyze mock data, when, for example, 1 million participants learn some studies and did some exercises, so after the semester we have the time series of all actions of students in the Coursera, for example, or maybe edX and so on. And then we also don't have explicit knowledge, but after the formal concept analysis we have non-explicit topics of interest for the students. We have the quality analysis, and very interesting case, we have cheating analysis. And then we can check the marks for this mock course and check the adequate if the final mark adequate or not. For now this is a very hot topic. So we have the very interesting common books in this area. The one I like with one guide to intelligent data analysis, how to intelligently make sense of real data. Very good title of this book. This is the book for the analytics, not the mathematics, or maybe for technicians. It's for end users. And for now we have additional books of this kind, but I didn't read it for now. But this book was read by me and I can recommend it. Also we have very interesting sites about the data analysis methods, and one of the example is the book section of data analysis and art. We have the very good annotated list of publications, textbooks with topics and text. So for now we have the very big background for implementing modern data analysis techniques in different domains. for now, we have the experience and fields of criminalistics, very interesting about the pedophiles and so on. Then we have the experience and field of internet data analysis. Then we have the experience in educational data mining and so on. And I think that we can help in data analysis and of course the not only formal data but any raw data analysis and the field of sociology and maybe additional fields. Thank you very much. I'm sorry that my healthcare not very good. Sorry one more time.
Thank you.
Thank you. And okay, now we have about 15, maybe maximum 20 minutes for questions, comments and discussion.
Yeah, most interesting part.
Unfortunately, the most interesting part was in the last half of your presentation, that you did very quickly and rapidly, and so it's really difficult to ask questions about that because of we didn't have enough time to really grasp what you're saying. But I wrote down some website addresses. I have a couple of questions from the first part of your presentation that was more, that was slower and also perhaps better structured. So, a clarifying question about rejection of the null hypothesis and then claiming equivalence. This is one of the typical mistakes, if I understood it correctly. Because in your presentation it said alternative, rejecting, not rejecting alternative. Too many slides.
Yeah.
I think it was later than this.
Later. Oh, yeah.
It's the type of common testing of hypothesis.
This lists, yes.
Oops, and where is... yes.
Yeah, here. Do you mean here really a null hypothesis rather than alternative hypothesis? This is the question that I wanted to ask. Because once we reject the null hypothesis, then we accept the alternative hypothesis, right? But if we do not reject the null hypothesis, then we should conclude that we don't know what's going on in the population. I just want to touch base with you if this is...
Yeah. In the standard case, we have two distinctive hypotheses, and so we don't have any alternative hypothesis at all, and this is the source of this mistake. So when we have only null hypothesis and appendix to it, then we don't have alternative hypothesis. And when we have alternative hypothesis, then we must additionally test each of alternative hypotheses. We don't have enough to check only the rejection of null hypothesis. Maybe such phrase is not complete, because the main source of error is the rejection of null, but not accepting the alternative hypothesis. We, for example, don't test it at all, but say that after rejection of the null hypothesis, we automatically accept the alternative.
Yeah, that's what I was taught when I was a student.
Could you please give us an example of such a mistake?
Of course. For example, the very classical situation, so-called placebo control study. When we have the placebo control study, we have additional group with placebo control. This is mean that we have actions in the conducting of experiment without real sense. This is so-called virtual actions.
Yes.
In the pharmacophy, this is the placebo buttons. So we have no
No,
real
No
Yeah.
treatment.
treatment, but we have all the protocol actions for the experimentation. And then we have three alternative hypotheses, because we have three groups. We have additional hypotheses for the equivalence to placebo, then we have hypothesis for superiority to placebo, and we have non-inferiority to placebo. And all of these outcomes should be checked
Right.
additionally.
Right. Oh, that is clear. Yeah.
And for example, when we have the survey about the president on next primaries, then we have also additional question. For example, we have some variants, Putin 1, Putin 2, Putin 3, and then other. And
What does mean Putin 1, Putin 2, Putin 3?
some variants of the president on next primaries. It's a trivial case. And then other. And so when we have simply other, then
It's good that we speak English here.
You don't have other,
Yeah.
just Putin now.
one Putin is enough.
That's
Maybe.
Sorry.
So if we simply have the point other in the one case, and if we have the text box with please write other candidate,
Yes.
then this will be
Oh.
additional.
Right. That is clear. Yeah.
So in the last example, we are talking about an additional test.
Yeah.
We
Yeah.
cannot accept the null hypothesis. We need to know what are the differences here.
Yeah.
Yes.
And without additional inference statistics for this difference, we don't have any consideration about it. We have only knowledge about the rejection of null hypothesis.
Yes.
The differences are exist.
Yeah.
Yes.
And so the most hardest part of all classical inference trials design is the non-inferiority, because superiority and equivalence in a common sense quite simple, but the non-inferiority it's very hard, because we in implicitly have additional hypothesis about the superiority, but we don't check it. But in many articles we have the conclusion with such considerations. Because, for example, I have such non-inferiority sample when we have some margin delta, and this is the margin with minus sign. And so if we have some point and the confidential interval excuse me, when the left limit of the confidential interval confidence interval to the right of this limit, yes, then we have non-inferiority. But there will be additional cases when we have non-inferiority, but with very interesting situation in case of equivalence. because in equivalence we have minus delta and plus delta, and so it's a straightforward situation. But in inferiority, the second case is very interesting. We have the point to the right of the left limit. Yes? And so if we don't have confidence interval, we can say, wow, we check the non-inferiority, it's good. But if we have confidence interval and the left limit of confidence interval to the left of the limit of the margin, it's bad. By all guidelines, this is not the situation of non-inferiority. But we have the trouble. In the simple case, when we check the normality, then we have so-called true confidence interval. And so the left and right limit of this interval is equal, yeah, and so with confidence interval very adequate to real situation. But when we don't check the normality of distributions, then standard confidence interval in the almost all article inadequate at all, because if, for example, we will use a special permutation methods for real calculation of non-parametric confidence interval. Do you know such algorithm now? When we have normal distribution, we have approximations for all statistics, for all classical statistics, t-statistics, he-statistics, and so on. And we have the simple formula for confidence interval. Wow, it's cool. But when in case where we have normality with hard tails, already in this case we have the troubles with classical confidence interval. But for example, when we have B-model distribution, then if we have average point mean between the two peaks, then we have very inadequate confidence intervals, all he distribution, t distribution, and so on. And of course, we have the algorithm by definition. We can permutate all the points in our sample with two groups, in confidence interval and out confidence interval, and then check the probability by Monte Carlo method. This is a very computational hard method. We need the very good computers for it, but this is the method that works in every situation, on every distribution. So, for example, in educational data mining, I need to use it because in educational data mining we have little normality, because in the group of students we have the max in every breath. So, in non-inferiority study, for example, in educational data mining, we have situations when we have standard interval, we have conclusion, wow, we have non-inferiority, but when I check the raw data, then I say, wow, your left limit of confidence interval is much righter. And so we, oh, excuse me, left, yeah, left. And so we don't have the real non-inferiority. And so your new educational methods is new educational method don't have normal
You can conclude that the new educational method is better than the old.
no, not better. Non-inferior to the old, yes, one.
Non-inferior.
So this is a very big problem. And because when we firstly discuss the, for example, ISSA, then when we try to read the methodology of PISA experiment, then we have several dark places where we don't have formal definition of models at all. And in 2013 we have very good article from Klein from Germany, and he had very good additional analysis of 2010 PISA experiment, and he discussed the mistakes in the formal analysis on the official site. And of course we have, for example, book Freakonomics. I think you read it. And there we have the very interesting situation with correlation and causation, because the normal models for experimentation didn't describe it at all, but in this book we have preliminary knowledge about the situation, then we have some discussion and results, and some results are quite good and some results are quite inadequate to the regression models. And so we have more than 6 books with discussion of some dark spaces or dark places in Freakonomics. It's a very interesting topic for meta-analysis. For example, in the Cochrane website, for now we have the new hot topic in meta-analysis of additional randomized control trials about the specific psychological methods of treatment. So we have also the this August article in Science with re-implementing the more than 200 of most influent psychological trials. And as a result of 4 years of re-implementing, we have the very interesting result. We have 50% of non-reintroducible results. So, in the psychology area, we have, as a joke, no knowledge at all.
Yeah,
because
it's 50-50.
50-50, yeah, it's absence of any
The
knowledge.
highest level one.
So this is a very beautiful article. It's very good. Yeah, excuse me. Oops.
What's there?
Веселятся.
Where is the sound?
I don't know, we don't hear.
Well, we have just maybe 1 minute left, and if we have any, if anyone has any short comments, so please. Otherwise, our time is expired. Yes, we have a short comment in St. Petersburg.
Yeah. Hi, I have just one question. Since we did not have enough time for the presentation, I really want, if you could please recap for us, what is the difference in one sentence between intelligent data analysis and just data analysis? If you could, put it in a nutshell, just one sentence.
Yeah.
Thanks.
One sentence. For now, we have 2 parts in data analysis. First, without additional knowledge, and with additional knowledge. So all statistical methods and all methods of simple posteriorization and summarization, non-intelligent methods, and all methods ontology controlled, all methods with formal concept analysis, with some linguistic methods, some semantic methods, called intelligent data analysis methods.
So, would all Bayesian statistics be intelligent because it uses some priors? By definition.
No, with priors are not knowledge about the domain, it's the knowledge about the selected model.
Mhm.
So it's main disadvantage of statistical methods, because we need to hold some model and then use this model without any change to this model. Any change to this model take us to the bad experiment. So if we have in the experiment design some statistical model, then oops, any additional knowledge does nothing. It's a very interesting point, because if we have the ability to append any additional knowledge to our model, then this is intelligent data analysis. But when we don't have any ability to append some knowledge to our model, then this is non-intelligent analysis. This is example. Excuse me.
Yes.
Maybe some examples.
No, no.
No. Thank you so much, Alexey. It's a pleasure to listen to you. And okay, thanks to everyone. And see you and hear you next Thursday. Thank you.
Thank you.